Okay, good morning. We are on lecture 10 today, and I have a question on homework 1, right? So I think your question is, the data files have, if I remember correctly, S, X, Y, UE or VINF or something like that, and then some other things. And your question is that the X goes beyond the trailing edge, right? So that means if you look at the data starts here, goes like this, around, comes here, and then goes this way. And that will happen for the viscous files. The inviscid files will stop here, but the viscous files have data not only for the boundary layer but also for the wake. So if I draw the boundary layer, right, so you have boundary layer data going all the way here on the upper and lower surfaces, and then there is a wake, and the data files have the wake data as well. And so for the purposes of this homework, you can ignore everything beyond the trailing edge. Okay, does that answer the question? Any other questions? So someone was asking what is S? I think in the Piazza discussion somebody was asking what is this S? S is basically the arc length, cumulative arc length from here to every panel endpoint. So from the upper trailing edge along the airfoil around to the lower trailing edge. That's what S is. Other questions?
You say that graph V with X over C. Can we graph UE over VINF, or do you really want us to like graph just the velocity at that point of the airfoil?
So UE over VINF is practically the same as
Right.
V over VINF, except that this will go negative, at least the way this data set is X-foil. This comes from X-foil, and X-foil sign convention is that if the flow is attached, then, well, even if, I mean, this is the outer flow anyway. So X-foil sign convention is it's all plus here. This is UE over VINF. And on the other side of the stagnation point, it's negative. But for our plotting purposes, this is also positive. But we just, because it's a data file from X-foil, it's got negative here. So, so to plot V over VINF, use absolute value or magnitude of UE over VINF.
Okay, but so the question I had was, you do want the non-dimensionalized velocity graph, right? Because you just had plot V. So I didn't know if you wanted me to find a free stream and multiply.
No. So correct. So when I say V, it usually is a short form for V over VINF. Okay. All right. So in the last class we started talking about boundary layer characteristics. We talked about laminar turbulent boundary layers. Right, so turbulent boundary layer has more skin friction, that's the bad part. But the good part is it's got more mixing, so it's able to go through more adverse pressure gradient before separating. So now we'll continue on that, and let's look at some factors affecting boundary layer separation, transition, etc. So what makes a laminar boundary layer transition to turbulent or separate, or what makes a turbulent boundary layer separate? Because these changes in boundary layer state very significantly affect how an airfoil performs in various conditions. Okay, so first let's start with the transition. So factors affecting transition of laminar boundary layer. Okay, so let's try to sketch the process. So you have laminar boundary layer flowing over a surface, and due to disturbances, and these disturbances can come in many forms. So it could be, for example, acoustic disturbances, or it could be some sort of roughness, acoustic, surface imperfections, etc. Right? So these disturbances will cause waves in the laminar boundary layer, and depending on the situation, these waves may get amplified and grow and eventually cause the boundary layer to become turbulent. And I'm just drawing these wiggles again more as a graphical representation. Don't think like the flow is actually going to do all those things. It's just very completely for the purposes of illustration. So what happens here is that waves of certain frequencies grow because of instabilities and eventually cause transition. So what we are going to do now is think about what are the factors affecting this process. So one of the main factors affecting transition is velocity gradient. Okay, so velocity gradient, as you know, is the same as pressure gradient. So what happens here is adverse pressure gradient promotes transition to turbulence. And conversely, favorable gradient delays transition. So maybe the easiest way to think through this is to look at two airfoils, one having favorable gradient and another having adverse gradient. So let's draw a CP distribution for two airfoils. Let's first consider this airfoil, which has got favorable gradient to nearly something like 60% of the chord. We're going to look at only the upper surface because that's the one of interest in this discussion. And then let's look at another airfoil where this airfoil has got adverse pressure gradient from much earlier along the chord on the upper surface. So on this we have something like this. So here you have favorable gradient to maybe 60%, so 0.6 chord, and maybe this is 0.3 chord, x over c of 0.3. And what happens is this favorable gradient, it starts off as laminar flow, right? All the boundary layer starts off as laminar boundary layer, and all along from the leading edge to 60% of the chord, it has favorable gradient here, and favorable gradient supports laminar flow. It delays transition. So transition will occur only at around 60% or 65% or something, where the adverse pressure gradient begins. So on this airfoil, transition will start somewhere here. But on the second airfoil, this laminar boundary layer encounters adverse pressure gradient earlier, like around 30% chord. So here transition will start at this point. So these are two airfoils at the same Reynolds number, but still, because of the way the pressure distribution is shaped, you have transition to turbulence at the point where adverse pressure gradient starts. So these are two upper surface CP distributions at the same Reynolds number. Okay, so the second factor is the chord Reynolds number of the airfoil. So what happens here is, if you have a larger Reynolds number, larger Reynolds number amplifies the waves caused by the disturbances. So we know that there are waves that are always excited in laminar boundary layer. Sometimes these waves are damped and no transition takes place, but other times these waves are amplified and eventually that laminar boundary layer will become turbulent. So when anything amplifies the waves, like larger Reynolds number does, then that leads to more unstable boundary layer. Unstable means its laminar is trying to become turbulent. Stable means laminar is trying to stay laminar. And so unstable causes transition at a smaller adverse pressure gradient. Okay. In contrast, lower Reynolds number damps out the waves. And this leads to a more stable boundary layer, and it delays transition. So in the earlier page we saw how when the laminar boundary layer encounters an adverse pressure gradient, it transitions. How quickly that happens depends on the Reynolds number. So if you have very low Reynolds number, even in the presence of adverse pressure gradient, laminar boundary layer will be stable and it will try to stay laminar for a longer distance than at a higher Reynolds number. So if you have a higher Reynolds number at the very onset of any adverse pressure gradient, it will become turbulent. Whereas if you have low Reynolds number, it will keep going into adverse pressure gradient without transitioning. Okay, and then factor number 3 is surface roughness, which you've all probably studied in some form or another. So as you can imagine, roughness promotes transition. Because roughness will cause these waves to occur in the first place, and if the waves are large enough, that will cause transition. So for example, the consequence of this is when using natural laminar flow airfoils, So especially when you use laminar flow airfoils, right? Wings have to be maintained. The surface smoothness has to be maintained. So this affects how the wings are fabricated, which is why NLF airfoils have started becoming popular after the advent of composite construction. And then even after the airplane is in use, it helps to clean the wings and remove bugs from the leading edge. So I'm not talking here about computer program bugs that you might be encountering. These are actual bugs that hit the leading edge during flight, and if you have these bugs sticking around, then they'll cause transition. So in the earlier days, right, so before maybe 1980s, 70s, 80s, most airplanes were constructed using metal construction, and they would have joints like this where you would probably have some kind of a spar. So I'm just drawing the skin, and you would have a spar like this of some sort, and maybe another skin would come here. This might be the rear part of the skin, and these would all be joined with rivets. Many of these airfoils were not laminar flow airfoils, and that's because these rivets and skin joints are imperfections, and at Reynolds numbers typical of those for manned airplanes, this would cause transition. So laminar flow would not be, it's not possible to sustain laminar flow with such imperfections. But with many modern sailplanes and general aviation aircraft, the construction is done with composite construction, and so you have a smooth skin with no external imperfections. So you have spars that look like this. Maybe the spar will be like this. And so the outside contour is often built in a mold, and that's smooth. So this doesn't have any rivets and stuff like that. So even though NLF airfoils have been, people have known about NLF airfoils since the 40s. NACA designed a whole bunch of laminar flow airfoils in 1930s, 40s sometime. But practical use of those airfoils in day-to-day aircraft was not possible because most of the wings were constructed like this. Okay, so many airplanes now are constructed like this, but even then, in routine use, you get accretion of bugs and some debris in the leading edge, which will cause transition. So on these kind of airplanes, if you want the benefit of laminar flow, people actually go and clean the leading edge every so often, especially if it's a competition sailplane. I mean, this laminar flow matters a big deal because they're usually competing with each other, and even a few small increase in performance matters. Okay, so we looked at where surface roughness is bad, right? Surface roughness causes laminar flow to transition to turbulent and increases skin friction drag. But there are situations where roughness actually helps. And sometimes roughness is added intentionally. Anybody want to mention something that you know? Where do you add roughness intentionally? Golf balls, right? And then other, yes. Okay, that I don't know if that's specifically for this, but it could very well be. Frisbee, so Frisbee leading edge has some ridges on it. So if you take the simplest case of a circular cylinder, flow past a circular cylinder, there's, depending on the Reynolds number, this flow could be subcritical or supercritical. So subcritical is where the Reynolds number is small enough that the laminar flow separates early. So flow boundary layer starts off as laminar, and if the Reynolds number is low, it wants to stay laminar, but then when it comes to the, let's say, the equator, it sees big adverse pressure gradient here and it separates right here, forming a big wake. So this is what happens here is separation, not transition. So S equals laminar separation in this sketch. And because the separation happens at the equator, you have a larger wake and high drag coefficient. So this is a smooth sphere or cylinder, it doesn't matter. The flow is more or less the same. If you go to a higher Reynolds number, then we just talked about how higher Reynolds number will make the laminar boundary layer more unstable. So what happens is at higher Reynolds numbers, and those are called supercritical Reynolds numbers, this laminar boundary layer will become turbulent somewhere around here, and the turbulent boundary layer will stick around into the adverse pressure gradient, and it will actually separate somewhere here down, maybe it will probably go down to half the downstream side and then separate, and then you'll have a smaller wake. But if you want a supercritical Reynolds number, you either have to increase velocity, and sometimes you don't have a choice, or you have to increase diameter, or you have to increase density, or do something like that. Sometimes you don't have a choice, right? Like if you're talking about golf balls, usually the ball diameter is fixed and the velocity is fixed, and so the only thing, you don't have control over Reynolds numbers. So in those kind of circumstances, what you want to do, what you would like to do is have turbulent boundary layer when the flow comes to the equator position. Because as we saw, turbulent boundary layer has more mixing, so it will plow through into adverse pressure gradient much more than laminar boundary layer. And so in those kind of circumstances, one can add roughness. Okay, so here's that same sphere at the same Reynolds number, but then let's say you add roughness. This could be a seam in a cricket ball or something. It could be dimples in a golf ball, any one of those things. And so boundary layer starts off at the stagnation point as laminar, and then it encounters this roughness. And depending on the Reynolds number, it might become turbulent immediately or a little downstream of this. So if it's very low Reynolds numbers, even after the roughness, it will stay laminar, but eventually it will become turbulent. So it might become turbulent, let's say here. And as I've done before, I'm going to use a wiggly line to denote turbulent boundary layer. Now turbulent boundary layer also encounters adverse pressure gradient at the equator, but it's got more mixing, more momentum, so it's able to go through into adverse pressure gradient some distance before it actually separates to form a turbulent wake. So this separation occurs here. So instead of at the equator, it occurs downstream, so smaller wake and lower CD. So this is a rough sphere or cylinder at subcritical Reynolds number. So here the S is turbulent separation. And this is transition. And this causes a big change in CD. So this is really used in these kind of circumstances. Roughness actually helps. So it's kind of counterintuitive till you kind of understand why it's happening. Usually you think roughness will only make things worse, but it helps in these kind of circumstances. So that's for a bluff body. There are times even in streamlined bodies like airfoils, roughness can help. And here we are talking about airfoils. So where this helps is at low Reynolds numbers. So we talked about laminar separation bubbles in the last class. So let's say you have an airfoil like this. At low Reynolds numbers, the laminar boundary layer wants to stay laminar because it's very stable, right? It does not want to become turbulent, but when it encounters adverse pressure gradient, it separates, and then the separated shear layer transitions, becomes a turbulent shear layer, and then becomes attached boundary layer. And so this is the laminar separation bubble. So this for example might be a smooth, thick airfoil at low Reynolds numbers. In such airfoils, you will have a laminar separation bubble. There's probably nothing you can do about it. So for example, the Reynolds numbers may be about 100K to 300K or something like that, or even less, 10K, yeah, let's say 10K, 10,000 to 300,000. So one of the things you can do is to add roughness somewhere near the leading edge. So if you have the same airfoil, so let's take the same airfoil and let's put some roughness here, intentionally put some roughness. So this roughness is sometimes also called a trip, because it sort of trips the laminar boundary layer. Sometimes it's called a turbulator. Because it makes the laminar boundary layer turbulent. So here you have, as before, you have laminar boundary layer, and now because of the roughness, pretty much right away after roughness or slightly downstream of the roughness, depending on the Reynolds number, it will become turbulent. And if the boundary layer is already turbulent, by the time it comes here, it won't form a laminar separation bubble, right? It will stay attached, and it might form a wake. It might separate a little bit early or not, depending on the situation, but at least the laminar separation bubble is avoided. So transition may be occurring here, for example. So this is a case where tripping the flow helps. And what we mean by tripping the flow is, this refers to intentional or unintentional do you use an S or T with intentional? I don't know, something. You know what I'm saying? Anybody know? Intentional. Looks correct, right? Yeah, okay. So intentional or unintentional use of roughness to cause transition from laminar boundary layer to turbulent. Okay. And then there may be some other factors. So people have been trying for some decades, actually, if there's a way to do flow control. So you could have, for example, suction or other types of flow control. So example is active wave cancellation methods. So these are much more lab kind of methods. I don't think they've ever come to the point where they've been applied on, say, vehicles. Maybe even then it would be probably in an experimental sort of phase. So here you may have an actuator at this point on the surface. So this is the surface. And you may have a sensor here, sensor, and some kind of a control system. And so this sensor may be something like some sort of hot wire or hot film or something like that. And it looks at what the waves are in the laminar boundary layer, or the signature of the waves, and then it will send some signals, appropriate signals, to the actuator to either cause transition or to cancel the transition waves, for example. Um, so there are times when you want transition, like if you have if you're going to have laminar separation, maybe this system could actually go and excite the laminar boundary layer by appropriate waves of appropriate frequency, and then the laminar boundary layer would become turbulent. Right? On the other hand, maybe you don't want transition, in which case maybe the actuator will give waves that are opposite to what the waves that are coming here. It's kind of like active noise cancellation in some headsets, right? It actually sees what noise is coming from outside and then it gives the opposite signal and cancels it out, something like that. So this is just one of those things that people have been trying for some time. And then there are some other factors, so I'm going to call this factors 5 plus. This could be free stream turbulence, for example in wind tunnels. It could be vibrations, it could be sound or noise. So one of the things people have seen with low Reynolds number airfoils, so for example airfoils that are used on model airplanes and radio controlled sailplanes, is it is so hard to get repeatable data. So if you put a model of an airfoil in some wind tunnel, you get the drag and lift at some angle of attack. And then you take the same model and go to some other wind tunnel, you get fairly different answers. And it bothered people for a long time until they realized that wind tunnels have free stream turbulence, right? Because there's a fan that's running and then the air is sometimes often going around. Even though you might put screens to remove or minimize turbulence, screens could do that, and then you also have honeycomb sections to remove turbulence. It's never the same between two different tunnels. So if you put a low Reynolds number airfoil in a highly turbulent wind tunnel, the laminar separation bubble may get tripped because of the free stream turbulence. And so that airfoil may actually have less drag than if you put it in a very clean tunnel, clean in quotes, clean meaning the flow is extremely low turbulence. Then the laminar separation bubble will be pretty big because the flow will be laminar, it wants to stay laminar. So that's one reason why turbulence intensity is something that's quantified in most tunnels. And then if you have vibrations, so on an aircraft, if you design an aircraft with NLF airfoils, but then there's so much vibration, maybe the metal skin is vibrating due to some, just the way the setup is, then that could cause laminar boundary layer to become turbulent. And then you could have sound and noise. So these are all different factors that affect laminar boundary layer transition. Okay. Let's look at laminar boundary layer separation. So this was transition, right? So this is affected by velocity / pressure gradient. This thing is going to come all over the place, this pressure gradient, velocity gradient. That's why we spent a little bit of time in the earlier lectures talking about what exactly that is and like just getting that defined properly. And sometimes by roughness. And it's really not affected by Reynolds number. So let's put some sketches together to think through what these factors are. Okay, so example of laminar separation. So let's take a natural laminar flow airfoil, something like this, where the CP distribution has favorable gradient till here, and then it has adverse pressure gradient. So this is the upper surface CP. And let's say this is Reynolds number of 3 million. Right, so here the laminar boundary layer, this is a fairly high Reynolds number compared to what we're going to look at in comparison. And here the laminar boundary layer is already, it's not very stable. So when it sees an adverse pressure gradient, it's going to become turbulent rather than separate, and so it becomes turbulent boundary layer, stays attached, and here you have transition. But if you take the same airfoil and now operate it at 100,000, which is like 0.1 million, right? This is 3 million, this is 0.1 million. Same airfoil. So for the most part, the CP distribution, let's say the inviscid CP distribution is going to be the same. That does not depend on Reynolds number, right? Something like this. Now, the Reynolds number is much lower than in the first case. So laminar boundary layer will not transition, because at lower Reynolds numbers, laminar boundary layer is very stable. It's hard to make it turbulent. So what happens is this laminar boundary layer is really stable, keeps wanting to stay laminar, and then it encounters adverse pressure gradient. At this point, it separates, right? And then it forms the laminar separation bubble, which we have seen before, and becomes like this. So the same airfoil at a lower Reynolds number will laminar boundary layer, instead of transitioning to turbulent, now it stays laminar, separates, becomes laminar shear layer, which after that it becomes turbulent and reattaches to turbulent boundary layer. So if you want to avoid this bubble, you can reshape this airfoil and avoid having so much favorable gradient all for so much distance, right? Favorable gradient keeps it laminar, and this Reynolds number, it automatically wants to stay laminar, so why bother with favorable gradient? So if I'll draw the third airfoil here. So if the blue, let's say the blue airfoil, I'm going to draw it in, see if I can find a different color. Okay. So I'll draw the blue airfoil, this airfoil in dashed line. So we had this airfoil like this. I'm only going to bother about the upper surface in this discussion. Now this airfoil with a dashed pressure distribution was like this, right? Now at low Reynolds numbers we don't want this. This would be good for high Reynolds numbers because high Reynolds number laminar boundary layer wants to become turbulent. So to keep it laminar, you give it favorable gradient, and then it's happy and stays laminar. But at low Reynolds numbers, this laminar boundary layer, it's hard to make it turbulent, so you have to work at making it turbulent. So what you might end up doing is something like this. If you want to keep the same lift, so you might do something like this. So this is an alternate better CP distribution to help promote transition. Because we know adverse pressure gradient helps promote transition. So you put an adverse pressure gradient from early on, and so this airfoil, maybe it'll look like this. So this picture is basically possible redesign to avoid laminar separation bubble, avoid or minimize. So even with this redesign, sometimes you can't avoid a laminar separation bubble, but it will at least be smaller than this case. That's one discussion. The other discussion is, let's take this same airfoil and instead of 100K, let's go to even lower Reynolds numbers, maybe 50K. Will the separation occur at the same place? Okay, so let's take a quick look at that. So if you take that same airfoil which we had at 100K and let's say this is at 50K. It turns out that the separation occurs at the same place. So in both these cases, laminar flows does not become turbulent, but instead separates and forms a bubble. But here also separation occurs at the same place. And now because it's a lower Reynolds number, even the separated shear layer, the laminar shear layer, even that has a problem becoming turbulent. It's just things are very stable. It wants to stay laminar even after separation. So you'll probably get a bigger bubble, and maybe it'll be like this. But anyway, the point is, onset of laminar separation is not dependent on Reynolds number. But only as long as transition does not happen upstream. So that's true in these two cases. The laminar boundary layer comes all the way to this point while being laminar, and so it becomes separated laminar flow. Okay. So we're going to now move on to turbulent boundary layer and look at what are the factors affecting turbulent boundary layer separation. So just to place us in our kind of outline, we've talked about these two, and now we're going to talk about turbulent boundary layer separation. Yes?
So you're saying that the onset of laminar separation does not depend on Reynolds number, but I mean, the characteristics of that bubble kind of do, right? Because they're bigger.
Yes. So separation is not affected. But what happens after separation is transition, right? In a laminar separation bubble, there's transition here. That transition is definitely affected by Reynolds numbers. So at higher the Reynolds number, sooner this transition will occur in the shear layer, and therefore smaller will be the bubble. Yeah, good point.
And when you say Reynolds number equals 100,000, you're talking about a free stream Reynolds number?
Yes, so in all these cases, I mean, there are many different Reynolds numbers, right? There is local Reynolds number based on X. There is boundary layer Reynolds numbers, sometimes based on momentum thickness and local velocity and things like that. Here we are refers to chord Reynolds number using free stream velocity. So that is RE, sometimes it's written as REC to avoid confusing with Reynolds number based on boundary layer thickness or something like that. Sometimes it's referred as RE infinity. I think I've seen it in some places. But basically what this is rho V infinity chord over mu, which is the same as V infinity chord over nu. Right, mu is dynamic viscosity coefficient, coefficient of dynamic viscosity. Nu, this is mu. This is kinematic viscosity. Keen. And this is nu, and this is really mu over rho. Okay. Any questions? Any more clarifications? Okay, then let's go and look at factors affecting turbulent boundary layer. Separation. velocity gradient always affects separation, whether laminar or turbulent. So velocity gradient is a big contribution. Velocity or pressure gradient. It's the same thing. And then Reynolds number. And upstream history. Or really, what is the momentum of the turbulent boundary layer at the point that you're looking at? So let's look at effect of velocity gradient. So to think about this, let's take two airfoils, a somewhat thin, a thinner airfoil and a thick airfoil. So let me draw a thinnish airfoil like this, and then I'll draw a much thicker airfoil like this, the same airfoil where the thickness is increased, and it looks like this. Again, we are focusing only on the upper surface just for discussion purposes. So let's say the thinner airfoil has a CP distribution that looks like this maybe. The thicker airfoil, because it is thick, there will be more suction on the upper surface, and then it will come back to the same place. So it'll have more suction, and then therefore it has to come down back to about the same point. So it has more adverse pressure gradient. So this region is adverse. The thicker the airfoil, the more it has to fall over that pressure drop. And for this discussion, let's assume the flow is turbulent right from the leading edge. So let's take this thin airfoil and look at the boundary layer picture. So because the airfoil is thin and we are assuming that turbulent boundary layer starts from here, and you could do that with roughness, for example. But because the adverse pressure gradient is only not as much as this particular airfoil will have attached flow throughout. And so for purposes of our discussion, we are assuming that this thin airfoil has adverse pressure gradient that just barely avoids separation. So if you just make this airfoil any thicker, now you have much more adverse pressure gradient, and so you're going to have separation, and that's what happens with the thick airfoil. Okay, so this is thin and this is thick. So this is the thick airfoil from here. And now, obviously this boundary layer, it's the same boundary layer, right? It's pretty much the same. From the leading edge you have turbulent boundary layer just like this, but now it's encountering much more adverse pressure gradient and it can't go all the way to the trailing edge and stay attached. So it separates and forms a separated boundary layer. So what happens here is so bottom line is and this is kind of intuitive. If you have a thick airfoil, you know that towards the back of it, it's going to have separated flow, whereas a thinner airfoil is going to have attached flow throughout, right? That's really what all we are talking about. Now, let's look at the effect of Reynolds number. This is not all that clear, but I think we can say that in general, higher Reynolds number and the reason is likely that it's connected with how thick the boundary layer is at lower and higher Reynolds number. So in low Reynolds number flows, boundary layers are thicker, and a thicker boundary layer, chances are it will separate more easily than a thin boundary layer, and that's why a higher Reynolds number turbulent boundary layer is less prone to separation generally. Okay, so we have one more effect, which is the effect of upstream history, and we'll talk about that, and then we'll put all these things together to see how we make use of these effects to design airfoils to achieve whatever characteristics we want. Usually we want the flow to stay attached and then give a lot of lift and low drag. But how do we do that? By manipulating the pressure gradient to achieve these boundary layer characteristics. So we'll see that in the next class. Thanks.